Good morning. This is the last topic on this substation earthing grid design. So I will be giving one more small example today and finishing this topic. Now I will be covering about an example related to a fault on a transmission line and how that leads to the rise in the potential of the ground within the substation and whether it is dangerous or not. So let us look at that example. Let's say we have a 220 kV bus which is fed by transmission lines. This is the transmission line, and then we have a 220 bar 66 kV transformer. This is the 66 kV bus. We have 66 bar 11 kV transformer. This is fed to the 11 kV switchgear. Let's say this is 160 MVA, this is 20 MVA. Now, I will just summarize the cases which we have considered for study previously also. The first one was a design case. We considered 40 kA fault current. It was the first case. Then we designed the substation for the second case, which was 28 kA. This is the transmission line. Let's say there is a fault somewhere in between the transmission line. Then there will be a fault current of approximately around 10 kA. This has been calculated previously. So this is case 3. This is case 4. And for a fault on 66 kV bus, the fault current will be approximately 14 kA. For the fault on 11 kV switchgear, the fault current will be approximately 19 kiloamps. So this is case 5. Now case 4 and case 5 need not be studied. The reason is, when there is a fault on this bus, the fault current returns back to the neutral within the same substation. This fault current from this bus returns back to the neutral of this transformer, which is nearby. It flows through the metallic path. It does not enter the earth. Only when the fault current flows through the earth, there is a ground potential rise. Same is the case here also. So we don't study the case, these two cases. And further, we have to consider the fault current which is the highest. So the highest fault current is 28 kiloamps. So because of these two reasons, this case need not be studied. And as I mentioned previously, this case of 40 kA was too conservative. We did not consider the fault current division. That's why the current was very high. So this was a more realistic case. Now coming back to this case, when there is a fault on a transmission line, the fault current is fed from two ends. One is from this end of the transmission line and one is from the substation. Based on the calculation, we found out that this was around 6 kiloamps and this was around 4.4 kiloamps. Now this 4.4 kiloamps causes the ground potential rise in our substation, whereas this 6 kiloamps causes the ground potential rise in the remote substation. So let us consider this 4.4 kA as the fault current. Now this 4.4 kA again has two divisions. One part of this current flows through the earth and comes back to the substation. The other part of this 4.4 kA flows through the earth wire on the transmission line and returns back to the substation. So we have to, in this 4.4 kA, first we have to find out the fault current division factor SF. So previously I have told this fault current division factor, there is an equation Z equivalent divided by Z equivalent plus ZS. So sorry, it is Z equivalent plus RG. So Z equivalent is Z equivalent we have calculated in the previous example is around 4 ohms and RG is around 0.47 ohms, and this gives us an SF of 0.894. What does this mean? This means 89% of the fault current flows back to the grid through the earth, whereas the balance 10% flows through the earth wire. So the grid current which we need to consider is nothing but 4.4 into 0.894. This is approximately 4 kA. So we need to consider this current to determine the ground potential rise. DF was 1. Now one more thing I want to say is, when we considered a fault here, we considered it for 1 second. In the case 2, we considered the fault for 100 millisecond. So this was for 1 second, this was for 100 millisecond. The reason was we considered the differential protection. Now when there is a fault here on the line, you see, when there is a fault on a line, the distance protection on the transmission line acts. So you have protection at both the end of the line. Let's say this protection, the primary protection does not act and the backup protection acts. So we can consider the tripping time as 600 millisecond, that is 0.6 second. So for a 0.6 second, the factor DF, which takes into account the DC offset, will be approximately 1. Okay. Now let me go back to, what is the tolerable step and touch voltage? The tolerable step and touch voltage. The tolerable step and touch voltage is given by this equation 0.116 by root t, where t is 600 millisecond, that is 0.6. Body resistance 1000 ohms, and this is the resistivity of the surface material, which is approximate, that is rho s, which is 2000 ohm meter. 0.72 is the factor CS, which we have found out in the previous example, and this is a constant 6 and constant 1.5 that needs to be considered for these two equations. So we get the step voltage approximately as 1443 volts. The touch voltage is approximately 473 volts. Please note this time t here is 0.6 second. So I have told how we got 0.6 second. Okay, so when the voltage in a substation on any metal body is more than 473 volts, that can be fatal. And when the step voltage is more than 1400 volts, that can be fatal. So we need to design our system in such a way that the voltages attained are below this value. Now let us check the voltages that are attained. The equation for the touch voltage that is attained, which is called the mesh voltage, is nothing but EM rho by LM Km Ki into Ig. Rho is 200. The Km constant is 0.17. We have found out from the previous example. Ki is 7.72. This and this I am already computed in the previous example, so I am not computing it again here now. And the fault current is 4084. How? Okay. You can see this here, fault current. This is the total length of the earth grid. (13,866 meters). So we get EM as 77.3 volts. So this is much less when compared to 473 volts. So the mesh voltage attained is under safe limits. Now similarly, let us check the step voltage. The equation for the step voltage is rho Ks Ki Ig by Ls, where rho is the resistivity, 200 ohm meter, resistivity of the earth. I told previously also, please note in this equation, in the tolerable voltage we have rho s, resistivity of the surface. In this equation where we determine the attained voltage, we have rho, the resistivity of the earth. So you should know the difference between the two. The constant Ks 0.515 found out from the previous example. Constant Ki 7.72, Ig 4 kiloamps. You should not write this as kiloamps, you have to expand it and write it in amps. The total length of the conductor to be considered for step voltage is not directly the length, it is given by a formula which we have found out in the previous example. Please look into it. This gives us 308 volts, the step voltage which is attained. You can see 308 volts is less when compared to 1400 volts. So the step voltage attained is also tolerable. So if there is a fault on a transmission line which is feeding the substation, and if there is a fault on a transmission line feeding the substation, we have found out that the fault current will be around 10 kiloamps. The fault contribution from our substation will be 4.4 kiloamps. The fault current which flows through the earth grid will be around 4 kiloamps, and this fault current causes a ground potential rise, and because of this ground potential rise, the step voltage attained is around 308 volts, which is below the tolerable value of 1443 volts. The mesh voltage attained is around 77.3 volts. This is below the tolerable value, which is 473 volts. Hence our design is okay. So this is about the substation earthing grid design. I have covered the basics, then I have covered the step voltage and touch voltage tolerable limits. Then I have covered the step and the mesh voltage which are attained. Then I have taken one example on the design case. Then I have covered one example on the 28 kA, that is the actual fault current, where I have also explained about the fault current division factor SF. And then I have taken one example on fault on a transmission line. Then two more cases, fault on a 66 kV bus and fault on 11 kV. I have just illustrated them. They need not be explained further nor investigated further. So all this has been explained. I've also prepared a manual on this earthing grid design. Please go through the manual and please go through these videos. And when you're doing the actual sizing calculations, please refer the IEEE standard also. So this is supplementary. The video and the manual are supplementary to them. Please use the standard also. If you have any doubts, please pose your question on the video, as well as you can ask questions on the manual. I will complete my topic on this. Please keep following this channel. BKES. Please follow the channel VKS Bangalore. Next I will be covering about earthing calculation and earthing design for industrial building, refinery, power plants, etc. Thank you.